From the 2002 studies revealing action maps for the motor cortex, Graziano followed up some incidental observations for defense reactions. When the monkey's elbow was fully extended, stimulation to a region in the motor cortex caused the arm to flex at the elbow. However, if the elbow began in a flexed position, stimulation to that very same region caused the arm to extend at the elbow. That is, the position of the arm, its proprioceptive input may have affected motor control via spinal circuitry. This perhaps reflects that motor control may be about the intention or outcome or goal of an action and involve proprioception rather than recruitment of any particular muscles. We review the Graziano et al. Study of 2004, mapping from motor cortex to biceps and triceps altered by elbow angle. Again, Graziano and colleagues stimulated the motor cortex, this time in regions related to arm representation. The monkey's arm was placed in 4 different postures, and EMG recordings were taken for biceps and triceps muscles. The 4 fixed elbow postures were extended, less extended, intermediate, between flexion and extension, and finally flexed. 6 locations in the central sulcus of the primary motor cortex were chosen. These locations were known for arm representation. They were stimulated at 200 Hz of 30 microamps for 400 milliseconds. Sites 1 to 3 relate to the dorsal aspect of the arm and therefore should evoke elbow extension and triceps activity. Sites 4 to 6 relate to the ventral aspect of the arm and should therefore evoke elbow flexion and biceps activity. First, stimulation at location number 1 in the primary motor cortex, that is M1. With the elbow extended, there was triceps activity but no biceps output. This pattern continued for all 4 postures. For location 1, there was increasing triceps activity with increasing elbow flexion. So you may think from these results that this location number 1 is concerned with initiating elbow extension. The more the arm is extended, the less triceps activity that is required to initiate elbow extension. And the more flexed the elbow, then the greater the triceps activity required to activate elbow extension. Second location. In the elbow extended position, there was equal activation of biceps and triceps, but thereafter, with increasing elbow flexion, the triceps were activated more than biceps. Third location. This time, with the elbow extended, the biceps were activated. This activation decreased for the less extended posture, and for the intermediate posture, biceps activity equaled triceps activity. And then in the flexed posture, triceps EMG was maximized. That is, muscle activation reversed from biceps with the arm extended to triceps with the arm flexed. So again, we might interpret these results that location 3 is intermediate between elbow flexion and extension. If the arm is extended, then stimulation of this location evokes elbow flexion with biceps contraction exceeding triceps activation. But when the arm is more flexed, stimulation of the same region now evokes greater triceps contraction than biceps. Finally, we speed up and move on to location 6. Here we see that it is biceps all the way, with greatest activity in the extended posture and less with increasing elbow flexion, and with minimal triceps activity throughout. This suggests that location 6 is concerned with initiating elbow flexion for any angle of the elbow joint. Graziano and colleagues state, in this hypothesis, proprioceptive signals about muscle stretch and elbow angle may have modulated the spinal circuitry in such a way as to alter the strength of the descending connections from cortex to muscles. And to conclude, they state, we suggest that these results of the present experiment may reflect a map of desired postures encoded in the motor cortex.